Look out across a continent that has never heard the sound of rainfall. The sky is wide, pale, and full of light, yet it never breaks. No storm crosses the horizon, no drops strike the dust, no dark clouds roll over forests, because there are no forests here, only stone, salt, and cracked ground stretching toward a heat-shaken distance. The air carries no smell of wet soil. Riverbeds lie empty before they are ever born, and in that strange silence, you begin to understand that rain is not just weather. It is one of the quiet forces that made the world livable. Without rain, Earth would not simply be drier, it would be transformed. Landscapes would erode differently. Fresh water would become rare far from the sea. Soils would struggle to form. Vast green interiors might never appear. The deep interiors of continents could turn into immense mineral wastelands, while life clings to coasts, mist, springs, and the few places where moisture can linger. Remove rainfall from the story of our planet, and you do not remove a detail. You remove a foundation. And because water on land decides where plants grow, where animals gather, and where people can survive, a rainless earth would feel primal in the oldest sense of the word. A world of thirst, distance, exposed horizons, and the constant knowledge that safety may exist somewhere, but not here for you right now. Science gives us a clear reason to take this idea seriously. Rain is part of the water cycle that links ocean, atmosphere, land, and life. It feeds rivers, shapes valleys, alters rock, moves nutrients, and helps build the soils that support ecosystems on land. Researchers studying climate, erosion, weathering, and ancient environments have shown again and again that falling water helped sculpt the continents we know. So tonight's question is speculative, but its logic is real. If Earth had oceans and an atmosphere, yet rain never became a normal way of returning water to the land, what kind of planet would that create? That is the path we are about to follow. Not a fantasy world with no scientific rules, but a plausible, alternate Earth built by removing one familiar process and tracing the consequences, slowly, carefully, and all the way down. We will move from sky to stone, from stone to soil, from soil to life, and from life to the possibility of civilization itself. If you enjoy these long journeys into Earth's forgotten possibilities, take a moment to like the video, subscribe, and tell me in the comments where in the world you're listening from tonight. I always love seeing how far these quiet documentaries travel. Now, dim the lights, settle in, and let the noise of the modern world drift a little farther away. Take a slow breath. Let your thoughts loosen, and together, let us step into a version of Earth where the clouds gather, the oceans breathe, and still, somehow, the rain never comes. Stay there for a moment beneath that patient sky, because the first thing you notice is not what this world contains, but what it withholds. The clouds can gather here. Vapor can rise from warm seas, drift inland, and fade into pale veils overhead. Morning mist may cling to a shoreline. Thin fog may settle in a valley before dawn. But the decisive moment never arrives. No cool rush passes through the air. No darkening cloud suddenly grows heavy enough to release itself. The long conversation between ocean and land is never completed. Water leaves the sea, enters the atmosphere, and then, somehow, fails to return
in the one way that shapes so much of the surface we know. To imagine a rainless earth properly, it helps to strip away the habits of the modern mind. We are used to thinking of rain as ordinary. It interrupts a drive, softens a garden, fills a gutter, blurs a window, delays a walk. But in physical terms, it is one of the great delivery systems of the planet. It brings fresh water far from coasts. It cools surfaces.
It feeds streams that join rivers, that cross continents. It seeps down into rock and soil. It dissolves, carries, loosens, carves, stains, rearranges, and deposits. It is small in any single instant, yet immense in cumulative power. Over years, centuries, and millions of years, rainfall does not merely wet the world, it edits the world. So, when that edit never happens, the change begins at the most basic level, with the look and feel of the sky itself. In our own world, rain is part of a dynamic atmosphere in which rising air cools, condenses, and often reaches the point where droplets form, grow, and fall. Different climates do this in different ways. Some depend on warm, humid air over tropical seas. Some depend on mountains that force air upward. Some depend on seasonal shifts, monsoons, storm tracks, or the pulsing boundary between warm and cold air masses. But the principle is familiar. Water vapor enters the air, condenses into clouds, and, when conditions allow, becomes precipitation. If we imagine a world in which rain never falls on land, then one of those familiar endings has been removed. Clouds may still exist, moisture may still move, yet the land remains unwetted by any broad, reliable descent of fresh water from the sky. That does not mean a perfectly dry atmosphere, and it does not require us to picture a fantasy planet with no moisture at all. Dew could still form where air cools against the ground at night. Fog could still drift in from the sea. Frost could still appear where temperatures allow. In a few places, condensation might bead on stone or collect on sparse surfaces, but these are meager gifts compared with rain. Dew wets only the thinnest skin of the world. Fog nourishes where it touches, but rarely with the volume required to sustain deep soils, large rivers, or broad inland ecosystems. Frost may preserve moisture for a moment, then release almost nothing. These are the economies of survival, not the abundance required to build great green continents. If you were standing on one of these continents shortly after sunrise, you would likely see a world with hard boundaries. The coast might still hold some life, because the ocean remains the great reservoir of moisture and moderate temperature. Sea breezes could carry damp air inland for a limited distance. Fog belts, like those that support unusual life in some dry regions of our own world, might provide narrow corridors of possibility. But beyond those margins, the land would begin to change its character very quickly. Colors would flatten, greens would retreat, the surface would appear mineral, exposed, unfinished. The skin of the planet would be less like fabric and more like bone. One of the most powerful consequences of missing rain is that the land loses its most familiar softness. In humid places on the real Earth, rainfall helps create the layers we call soil, loose, living mixtures of weathered mineral grains, organic matter, air, water, fungi, microbes, roots, and chemical traces from long interaction between life and rock. A forest floor is not just dirt. It is the memory of thousands of wet seasons, of falling leaves decomposed by moisture and time, of minerals dissolved and moved downward, of roots opening small passages into the ground, of microscopic communities thriving in films of water. Remove rainfall,
And that whole slow conversation is weakened from the start. What lies underfoot is more likely to remain a shallow veneer of dust, grit, salts, and broken rock, easily disturbed, easily blown away, and much less capable of storing life. This matters because continents are not naturally soft. Rock, left to itself, is stubborn. The deep transformation from rock to rich soil requires weathering, and rain is among the main agents of that change. Physical weathering can break rock apart through heat, cold, salt growth, and mechanical stress. Even a dry world would still have temperature swings.
Rock faces would expand under intense daytime heat and contract in cooler nights. Salt crystals could grow in cracks where moisture occasionally lingers and evaporates. Winds loaded with fine particles could sandblast exposed surfaces. These processes would still sculpt the land, but chemical weathering, the quiet dissolving and reacting that rainfall so often drives, would be greatly reduced across most continental interiors. On the real Earth, slightly acidic rainwater seeps through minerals and helps transform them. Water enters fractures, reacts with exposed surfaces, releases ions, creates clays, weakens structures, and carries dissolved material away. Streams and rivers then transport some of those products into floodplains, lakes, deltas, and eventually the sea. This is one reason landscapes with abundant rainfall can become rounded, layered, fertile, and geologically expressive. Not all such landscapes are gentle, of course, but they are active in a fluid way. A rainless Earth would be active differently. Its land would weather more slowly in some respects, more harshly in others, yet with far less of the chemical deepening that makes soil thick, valleys intricate, and biological productivity possible over huge areas. The absence of rainfall also changes how a continent announces itself from above. Think of the great patterns visible in satellite images today. River systems branching like veins, broad floodplains, wetlands, mountain snowmelt feeding distant lowlands, forests responding to seasonal rains, belts of savanna and grassland shifting with moisture. So much of the continental map is really a map of moving water. Remove rain, and many of those patterns vanish before they conform. You might still have coastlines, mountain ridges, volcanic plateaus, basins, fault scarps, and inland depressions. You could still have groundwater in places, springs in others, and perhaps some lakes fed by special local circumstances. But the large dendritic logic of rivers spreading from wet heights to lower plains would be missing or drastically reduced. Continents would look less vascular, less nourished, and more abrupt. At this point, a careful distinction is useful. A world without rain is not necessarily a world without all fresh water. Water can reach the surface through routes other than precipitation. Groundwater may emerge as springs where rock layers and pressure conditions allow. Volcanic and tectonic regions can release water and other fluids from depth. In cold enough environments, ice may store ancient moisture. Coastal fog may condense on surfaces. Some basins might receive runoff from rare melting events if snow or ice were part of the scenario, though in the version we are imagining, widespread precipitation of all kinds across land is absent or negligible. So, fresh water is not erased. It is localized, intermittent, difficult to reach, unevenly distributed. And because it is localized, life and geology alike are forced into a patchwork rather than a connected continental system. That patchwork quality would influence even the atmosphere above the land.
In the real world, moist soils, vegetation, lakes, and rivers help shape local climates. Plants release water vapor through transpiration. Wet ground cools differently from dry ground. Forests alter wind and humidity. A storm may arrive from elsewhere, but the land it passes over can strengthen or weaken what happens next. On a rainless Earth, much of that feedback loop is diminished. Dry ground heats quickly. Sparse vegetation, if present at all, contributes little moisture to the air. Air masses crossing inland regions encounter fewer wet surfaces from which to regain humidity. The interior becomes self-reinforcing in its dryness. It is not simply deprived once, it remains deprived. This is one reason deserts on the real Earth can become stable over long periods when broader climate patterns favor them. In our scenario,
However, we are not speaking about deserts as one biome among many. We are speaking about continents whose default condition drifts toward aridity unless rescued by some unusual and local source of water. That would produce landscapes both familiar and unfamiliar. Familiar because we know dry valleys, salt pans, stony plains, dune fields, and exposed bedrock from places on our own planet. Unfamiliar because those environments would no longer be exceptions framed by wetter neighbors. They would become the dominant language of land itself. Imagine, then, the first major mountain range rising on such a world. Tectonic forces still lift crust. Continents still collide, stretch, crack, and wrinkle. Volcanoes still build cones and plateaus. Earthquakes still fracture stone. None of that depends directly on rain. A rainless Earth could still have dramatic relief. Jagged peaks, uplifted blocks, broad highlands, escarpments, and basins trapped between them. But the way those mountains age would be altered. On our world, mountains are worn down by glaciers, rivers, landslides, freeze-thaw action, and persistent rainfall. Their sediment is carried outward and downward, sorting itself into fans, plains, channels, and deltas. In a world without rain, gravity and wind take on a greater role in the visible dismantling of high ground. Rockfalls would still occur, slopes would still fail, but instead of feeding constant river systems, much of the debris would accumulate locally in dry fans and aprons, or be ground into finer material and moved episodically by wind. The valleys between those mountains would also feel different. Many valleys on Earth owe part of their shape to running water. Even where tectonics initiated the space, rivers widened it, deepened it, organized sediment within it, and connected it to a larger drainage network. Here, many valleys would remain discontinuous, closed, or dry. Some might resemble immense channels without active water. Forms inherited from rare events or ancient conditions no longer sustained. Others might never develop into the elaborate branching systems we take for granted. The silence of such valleys would be difficult to ignore. A person walking through them would see evidence of gravity, fracture, and wind, but little of that persistent liquid traffic that elsewhere turns a landscape into a system. And then there is the coast, the narrow band where the rainless continents would still meet a restless hydrological world. The sea would continue to evaporate. Waves would still attack cliffs, rearrange beaches, and move sediment along shorelines. Tides would still flood and retreat. Storm surges could still drive seawater inland. Salt spray could still travel on the wind. In many places, the coast might be the most active, habitable, and biologically rich part of the continent. But it would also be a deceptive edge. Looking inland from a moist shoreline, one could imagine that fertility extends farther than it does.
A thin green belt might fade in just a few kilometers. Then the moisture would drop away, and the old mineral face of the land would return. This coastal dependence matters because it limits scale. A continent can be broad and productive only when moisture crosses it. Rain performs that distribution. Without it, even a vast landmass remains hydrologically narrow. Its oceanic edge may live, but its interior empties. On real Earth, some of the most important river systems begin far from the sea and make the deep interiors of continents inhabitable. They allow forests, grasslands, floodplains, wetlands, and eventually agriculture and cities far inland. In our scenario, that interior lifeline is absent from the start. Any richness that survives does so in islands of circumstance, not as a continent-wide condition. The concept becomes even more striking if we follow the water cycle itself. Normally, solar energy evaporates water from oceans, lakes, soils, and plants.
That vapor rises, cools, condenses, forms clouds, and falls again as rain or snow. Some runs off into streams, some infiltrates into the ground, some is used by organisms, some evaporates again. It is a circulating system, never perfect, never evenly distributed, but continuous. If rain never falls over land, then one of the essential return pathways is blocked. Water still evaporates from the ocean, but the atmosphere delivers little or none of it in a form the land can store at scale. The cycle keeps turning, but the continents become poor receivers. They sit beside abundance and remain thirsty. This failure of delivery would have a profound effect on groundwater as well. Much of the groundwater we rely on today comes, directly or indirectly, from recharge by precipitation. Rain and snowmelt seep downward through soils and porous rock, replenishing aquifers over timescales that may be seasonal, annual, or geological. In a rainless world, broad aquifer recharge would be drastically reduced. Some groundwater might still exist as ancient water trapped from earlier conditions, water associated with tectonic processes, or water entering from limited zones of condensation or seepage. But once extracted or exhausted, it would be far harder to replace. Aquifers would become more like inheritances than incomes, stores that can be drawn down, not cycles that are reliably renewed. That distinction changes the emotional texture of the landscape. A renewable river suggests continuity. An old aquifer suggests countdown. Even if the planet has no people yet, the physical truth is the same. Water stored in rock, isolated in basins, or hidden beneath gravel plains becomes a treasure precisely because it is not visibly replenished. Springs would be miracles with geological explanations. Oases, where they existed, would be boundaries between possible life and near immediate stress. A map of the land would become a map of scarcity. Scarcity also intensifies the role of salt. When water appears in dry landscapes and then evaporates, it tends to leave dissolved minerals behind. Over time, salts accumulate in soils, flats, and basins. Without regular flushing by rainfall and rivers, this accumulation can become severe. On our own planet, closed basins in arid regions often end as salt lakes, playas, or mineral crusts because water arrives but does not escape to the sea. In a world with almost no rainfall over land, that pattern could become much more widespread. Large interior depressions might evolve into bitter flats where groundwater or occasional condensation brings traces of moisture only to lose them again under the sun. White mineral skins could cover the ground,
crystals might form in cracks. The land would glitter in places, not with life, but with residue. These salt-rich surfaces tell us something important about what is missing. Rain does not only supply water, it also moves dissolved material onward. It flushes, it redistributes, it prevents landscapes from becoming purely accumulative in one direction. In the rainless world, many continental interiors become chemical dead ends. Minerals arrive through weathering, seepage, occasional local water movement, or atmospheric dust, but they are not easily carried away. This creates surfaces that are hostile to roots, hard on the feet of animals, abrasive to skin, and difficult for ecosystems to soften. The very ground begins to remember dryness. So far, we have stayed mostly with the immediate consequences visible on the surface, but rainfall also influences the deeper chemistry of the planet, and that too shapes the look of the world over long spans of time. When rainwater interacts with rock, especially silicate minerals, it participates in processes that remove carbon dioxide from the atmosphere over geological timescales. The chemistry is complex,
but the broad idea is simple enough. Weathering helps lock atmospheric carbon into dissolved products that can eventually end up as sediments and carbonates. This is one of the mechanisms that contributes to Earth's long-term climate regulation. If rainfall over land is sharply reduced, then one major route of chemical weathering is weakened. The result could be a planet less efficient at drawing down carbon dioxide, all else being equal. That does not let us predict a single exact climate, because climate depends on many factors: volcanic outgassing, continental arrangement, solar luminosity, ocean circulation, atmospheric composition, planetary albedo, and biological feedbacks, among others. But it does give us a reason to take the dry world's heat seriously. Without regular rainfall, and with reduced continental weathering, large land areas could stay both dry and warm, perhaps very warm, for long periods. Dry surfaces would also tend to produce strong daily temperature swings, becoming brutally hot by day and losing heat more quickly by night than humid landscapes do. The viewer walking through such a world would feel both kinds of exposure: the hammer of sunlight and the chill that arrives after sunset when there is little moisture to soften the fall in temperature. The wind would have a larger voice here, not because wind disappears from wet worlds, but because rainless surfaces offer so much loose material and so little binding vegetation. Dust would be plentiful. Fine particles, lifted from flats and dry basins, could travel vast distances. In some regions, sand seas might organize themselves into broad dune fields, always shifting, always recording the balance between grain size, topography, and prevailing winds. Elsewhere, deflation would strip fines from the ground and leave pavements of pebbles and stones behind, surfaces armored by the very process that removed everything smaller. The air itself might carry the signature of the continents far out over the ocean in persistent plumes of dust, a reminder that dryness exports matter even when it cannot export water. Dust changes more than visibility. It can alter how much sunlight a surface reflects. It can fertilize oceans when it settles into them, potentially influencing marine productivity. It can affect breathing, abrasion, and temperature at the local scale. It can also create landscapes of burial, where old surfaces vanish beneath drifting sediment and reappear only after later winds uncover them. A person living in such a world would not experience the land as fixed. In the absence of rain, the continent would not become static. It would become mobile in a different way, moved grain by grain through the air.
This leads to a subtle but important point about beauty. We often associate rain with drama and dryness with monotony, but a rainless earth would not necessarily be visually dull. It could be starkly beautiful. Mountain shadows might cut across plains with extraordinary clarity in the dry air. Salt flats might shine like ice under the sun. Dune ridges could march in elegant parallel arcs to the horizon. Rock layers, unhidden by soils or forests, would reveal the deep architecture of crustal history with unusual honesty. Colors might be spare but intense: iron reds, sulfur yellows, chalk whites, black volcanic fields, violet dusk over pale stone. Yet that beauty would be the beauty of exposure, not shelter. The land would seem magnificent and unconcerned. And still, the greatest difference between this world and ours may be heard rather than seen. A rainless continent has no weather drumming on roofs, no patter through leaves, no hiss on warm stone, no swells of runoff entering creeks, no steady murmur of streams fed by distant hills. Soundscapes would reorganize around wind, waves, shifting sand, insect movement near water, perhaps the distant cracking of heated rock,
and long stretches of stillness. Even where the coast remains active, the interior loses one of the most repeating sounds in the history of terrestrial life. There would be no seasonal return of storms to set a rhythm for growth and rest, no afternoon shower to cool a plain, no distant thunder promising relief. This absence would shape the pace of geological change in ways that are easy to underestimate. In the real world, one heavy storm may alter a slope, flood a basin, strip a bank, and leave little trace centuries later, because later storms continue the work. In the rainless world, change may come in rarer, more localized pulses. A rock face collapses. Wind removes the finer debris over years. Salt works deeper into a fracture. A spring shifts course underground, and a patch of surface dies. The continent ages not by repeated washings, but by attrition. It is filed down, not rinsed. Yet we should be careful not to turn this into an image of total geological paralysis. Even without rain, time remains vast. Tectonics continue. The ocean continues to work at its margins. Temperature cycles continue. Rare local waters continue to seep, deposit, and dissolve. If the planet has ice in cold regions or on high peaks under this scenario, meltwater might still create special cases of incision or sediment transport, though much would depend on how precipitation as snow is treated in the thought experiment. The important thing is not that all wet processes vanish, but that they lose continental reach. Their geography collapses into exceptions. Exceptions are powerful. On a rainless Earth, every exception stands out. A spring line at the base of a cliff becomes a green scar visible for kilometers. A groundwater-fed wetland becomes a biological archive, a place where sediments, pollen, mineral layers, and bones might accumulate precisely because water is so unusual. A fog-nourished ridge near the ocean becomes a ribbon of life suspended between sea and desert. Such places would have disproportionate scientific value because they reveal the contrast between what the planet is generally like and what it can briefly become when liquid water lingers. They would also remind us that the story of this world is not simple absence. It is asymmetry. Water exists, but almost always in the wrong place, the wrong amount, or the wrong form for continental abundance. If we look far back in Earth's own history, there is another reason this scenario is interesting.
The earliest continents were not always covered in the rich soils, forests, and grasslands that later came to seem ordinary. Land has had to be transformed over time by atmosphere, weathering, biology, and plate tectonics acting together. The bare mineral face of early Earth was, in some respects, closer to a world of exposed rock than the familiar landscapes of later ages. Our speculative planet preserves something of that austerity, but indefinitely. It is as though the continents never fully crossed the threshold into lush maturity. They remain geologically present, atmospherically exposed, and biologically underwritten. That threshold matters because rain is one of the forces that allows land to become more than elevated crust. A continent is not simply a mass of rock above sea level. In the fullest sense, it is a system that stores and moves water, builds soil, hosts life, and exchanges material with ocean and atmosphere. Rain binds those functions together. It gives inland places a future. Without it, the deep interior of land remains a kind of unfinished sentence. Uplifted, yes. Exposed, yes. Sometimes magnificent, but not fully transformed into a self-sustaining green world. Nowhere is that more apparent than in the fate of rivers that never begin. On the real Earth, a river often starts humbly, seepage on a slope, snowmelt in a hollow, a wet patch where water gathers and chooses a direction. From there, channels form, tributaries join, valleys deepen,
and entire regions become legible through drainage. A river is one of the most democratic structures in nature. It gathers scattered drops and gives them a common path. In the rainless world, that gathering cannot happen at continental scale. There are no ordinary headwaters on distant hills waiting for the season to return. There may be springs, there may be short runs of water, but the great collecting logic of rainfall is gone. And without collecting, there is no grand release into the sea. The implications multiply outward. No broad alluvial plains built by recurrent floods. No rich deltas fed by huge sediment loads from inland basins. No vast meandering systems cutting through lowlands. No freshwater corridors allowing the deep interior to communicate with the coast. Sediment still moves, but differently. Coastlines may receive more from erosion at their margins than from river delivery from the heart of continents. Basins may trap what rivers would otherwise export. Mountain fronts may wear skirts of coarse debris instead of feeding integrated networks. Looking at such a world from orbit, you might think it had been drained. In fact, it was never watered. Even the colors of weathered rock would evolve differently. In humid climates, chemical reactions can produce thick lateritic soils, clays, iron-rich crusts, and deeply altered profiles. In cold, wet climates, freeze-thaw and waterlogging create other signatures. In this drier world, many surfaces remain closer to raw bedrock or thin regolith. Oxidation still occurs where air and limited moisture allow, but thick, biologically active weathering mantles are rarer. The result is a planet whose geology is often closer to the surface, less hidden beneath life. That could make the crust easier to read for a geologist, but harder to live on for almost everything else. And so, little by little, the image sharpens. Along the margins of the ocean, the air can still feel alive. Mist may silver the morning. Salt hangs on the breeze. A few hardy communities of organisms may gather wherever moisture pauses, but beyond that edge spreads a continent with a fundamentally different metabolism. It does not drink. It sweats heat by day and radiates it by night. It erodes, but not in the flowing way we know best.
It stores minerals, dust, and salts more readily than it stores fresh water. It lifts mountains without feeding rivers from them. It makes basins without easily filling them. Its beauty is severe. Its generosity is local. Its interior is not empty in the absolute sense, but empty of the one repeating gift that teaches land how to become habitable at scale. By now, the viewer can perhaps feel the true strangeness of the premise. Oceans still breathe water into the air. Clouds still decorate the sky. Condensation still happens in small and fragile ways. Yet the land remains excluded from the abundance next door. That exclusion shapes every rock surface, every basin, every plain, every ridge. The great green version of Earth that lives in our instincts begins to look less inevitable, more contingent, more dependent on a simple fact we rarely honor, that water must fall before continents can live. And once that fact is removed, another question begins to press forward from beneath the stone. If the continents stay this dry, this exposed, this chemically and hydrologically limited, then what kind of skin can life ever build upon them? What sort of soil can emerge? What sort of plants can hold? And how far from the sea can any living world truly spread? It is there, on the thin boundary between bare ground and the first persistent growth, that the story becomes even more revealing. Before we cross that boundary, it is worth lingering over the practical experience of moving through such a continent, because motion itself reveals what the geology has done. Travel inland would not feel like moving across a stable tapestry of biomes.
It would feel like leaving the last negotiable edge of the planet. Near the shore, surfaces might still be packed by salt moisture and occasional condensation. There could be stretches of gravel, darkened briefly at dawn, low succulents or lichen-like films where fog is dependable, and hollows where a little organic matter gathers. But every step away from that maritime influence would make the ground more brittle, more powdery, or more fiercely crusted. Footprints would either vanish almost immediately in dust or remain for a very long time on undisturbed flats because so little happens to erase them. This is another service rain performs without asking for notice. It refreshes surfaces. It blurs sharp edges, settles dust, resets tracks, redistributes seeds, softens hard pan, and writes over the record of yesterday. In the rainless world, surfaces remember for longer. A trail of stones displaced by an animal could remain visible long after the animal has gone. Wind would alter it eventually, but wind edits selectively. It strips one place, heaps another, and leaves many marks half preserved. The continent becomes an archive of exposure. To walk there is to move through traces that have not been washed away. In lower basins, where topography gathers whatever little moisture can arrive, the contrast would be sharper still. Some depressions might hold shallow brines fed by groundwater seepage from far older hydrological circumstances. Others would dry into mosaics of polygonal mud cracks and mineral crusts, not because rain recently evaporated, but because small pulses of subsurface water reached the light and were immediately taken back by heat and air. On our own planet, such places are among the most visually alien landscapes on Earth. Here, they would no longer be marginal curiosities. They would become standard continental features, recurring again and again, each one a lesson in imbalance. The mountains, too, would teach that lesson in a quieter language. In wet ranges, streams descend in countless threads. They announce slope, volume, season, and relief. In dry ranges, relief is shown more by shadow and debris than by water. Talus slopes widen, fans spread at canyon mouths. Dry channels, if they exist, remain empty lines waiting for a flow that almost never comes. The eye learns to read topography without expecting liquidity. Even color tells a different story. Dark varnishes may slowly build on exposed rock faces where chemistry and dust interact over long spans. Pale scars mark newer fractures. Rust tones reveal oxidation. But few of these signs suggest renewal. They suggest endurance. With so little rain to move dissolved minerals downward through thick soils, the surface chemistry of the land would become patchier and often harsher. In some places, salts would wick upward as groundwater evaporates, making the topmost layer hostile to most roots. In others, caliche-like hard layers could develop where minerals precipitate within shallow sediments, turning the ground into something between soil and stone. Such crusts exist in arid parts of the modern Earth and can be remarkably resistant. On a continent where dryness dominates, they could become widespread barriers, limiting infiltration, anchoring some surfaces while making others crack into sharp plates. The world underfoot would often feel armored, but not alive. All of this means that when we speak of a planet of dust, salt, and stone, we are not using poetic shorthand. We are describing a real physical shift in what the continents are made of at the surface and how they behave through time. Dust comes from the breaking and stripping of unprotected ground. Salt comes from evaporation without flushing. Stone remains visible because the processes that normally bury it beneath richer, wetter layers are weakened. Together, they produce a land that is geologically legible and biologically reluctant. It can exist for millions upon millions of years.
It can host local miracles, but it does not easily turn itself into a generous terrestrial world, and that reluctance may be the most important thing to carry forward. A rainless Earth is not simply Earth with fewer storms. It is a planet whose continents never receive the steady invitation to deepen, soften, and connect. The sky offers shape without gift. The ocean offers abundance without access. The land waits under light, largely unchanged by the mercy that, in our own world, falls drop by drop. To understand what comes next, we have to ask what life can do with a surface like that, and whether the first persistent green footholds would be enough to change the chemistry, texture, and destiny of the continents at all. Perhaps that is the deepest strangeness of the world so far. Nothing essential is missing from the planet itself. There is rock, ocean, air, sunlight, tectonic energy, chemistry, time. The usual ingredients are all present, and yet one interrupted exchange between sky and ground leaves the continents bare enough that every later chapter of Earth's story must struggle to begin. The next question, then, is not whether water exists, but whether life can seize these rare pockets of moisture, patiently alter the surface, and teach a silent land to hold more than exposure. Because once the geology is this severe, biology no longer arrives on an easy stage. It enters as an experiment, fragile and local, trying to turn mineral skin into living ground. Whether that attempt succeeds and how far it can spread away from fog, springs, and coasts is where the dry planet begins to reveal its next secret. That experiment would begin almost invisibly in the thin film between mineral surface and the first persistent trace of moisture. Picture a slab of exposed stone near the coast, touched by fog before dawn and warmed again after sunrise. For most of the day it seems dead,
a hard face of the continent with no promise in it.
Yet, within tiny pores and sheltered cracks, chemistry and life can still meet. Microbes do not need a meadow. A lichen does not require a river valley. A crust of simple organisms can begin with very little, provided that little returns often enough. So, the first green or dark living stain on this rainless earth would not spread across open plains like a conquering forest. It would arrive quietly, close to the sea, wrapped in mist, rooted in crevices, surviving more by patience than by abundance. To understand why that matters, it helps to remember what soil really is. Soil is not loose rock waiting to be stepped on. It is a long collaboration among weathering, water, atmosphere, and life. Minerals break down into smaller particles and new compounds. Dead organic material accumulates and is transformed by decomposers. Pores form, collapse, and reform. Water carries dissolved elements downward, sideways, and upward again. Roots pry open cracks and leave behind channels when they die. Microbes alter pH, cycle nutrients, and bind particles together. Even in dry places on the real Earth, soil can still be intricate and alive, but it usually depends on pulses of moisture strong enough to wet more than the upper skin of the ground. Without rain, that wetting becomes sporadic, shallow, and intensely local. The continent may host patches of living surface, yet struggle to build the deeper, broader soils that allow whole landscapes to become productive. In our world, a steady supply of rainfall allows the land to remember seasons in layers. Wet periods swell microbial activity. Plant litter softens and darkens. Fine roots thread through the upper ground, then rot and feed new cycles. Dissolved minerals are redistributed downward, concentrating in some horizons and leaving others lighter. Worms, fungi, arthropods, and countless microscopic agents mix and remold the result. It is a slow architecture, but one with enormous consequences. A deep soil stores water.
It buffers temperature. It keeps nutrients within reach of roots. It allows one generation of plants to make the next easier. On a rainless earth, that self-reinforcing generosity is difficult to establish. Soil remains young for longer, thinner, poorer, more vulnerable to being stripped by wind or poisoned by salt. The surface can support life briefly, but less easily invite life to expand. That is why the first true biological drama of this world would not be the rise of giants. It would be the struggle to make a stable skin. Imagine walking inland from a fog coast at dawn. Behind you, the ocean is still exhaling moisture into the cool air. Ahead of you, the continent seems pale and withdrawn. On some stones, you notice a dark varnish of life, perhaps microbial gnats or lichen-like associations nourished by condensation. In hollows, a little dust has gathered among pebbles, and because that dust traps a trace of organic matter and shade, it stays usable for a little longer after morning dampness fades. Near certain cliffs, springs fed by deep groundwater create ribbons of soft sediment where small plant communities might dare to persist. Each of these places is a biological foothold. Each is also a warning. Step beyond the narrow influence of recurring moisture, and the living skin thins almost to nothing. The plants that manage to survive in such a world would be under relentless pressure to economize. On the real Earth, even in deserts, plants show extraordinary adaptations to water scarcity. Waxy coatings, reduced leaves, deep roots, rapid life cycles, dormant seeds, water storage tissues, and photosynthetic tricks that limit water loss. Those examples remind us that life is inventive.
A rainless Earth would not be plantless by definition, but the question is scale. Adaptation can help an organism survive dryness. It cannot magically create broad, productive inland ecosystems without a reliable source of fresh water.
So, while specialized vegetation might cling to coasts, fog zones, spring lines, and groundwater oases, the continental interior would resist full botanical conquest. There could be islands of green. There would be few green worlds. This distinction is crucial because when we speak of plants colonizing land, we are also speaking of them altering the land. Plants do not simply occupy a pre-existing environment. They change albedo, trap sediment, shade ground, cool surfaces through transpiration, feed decomposers with litter, and increase the amount of carbon stored in biomass and soils. Even sparse vegetation can reduce wind erosion. Dense vegetation can transform whole basins. In Earth history, the spread of plants onto land was one of the most important changes ever to affect weathering, soil development, atmospheric chemistry, and the structure of habitats available to animals. In this speculative planet, that spread would be stunted. The land would keep waiting for a biological revolution that never fully arrives. You can almost see the line where the attempt fails. A coastal fog belt might support low shrubs, strange fern-like forms, or tough vascular plants adapted to gather water from air and cling to shallow soils. A spring-fed plain could host grasses or mats around reliable seepage. In a mountain hollow, where night cooling encourages repeated dew and runoff from hidden aquifers gathers below the surface, a modest woodland might stand for a time. Yet, beyond these pockets, the atmosphere gives too little, the soil holds too little, and the salts gather too readily. Seedlings fail, not because life lacks ingenuity, but because the system around them withholds volume. Rain is not merely a trigger for germination, it is the repeated grant of possibility by which landscapes are slowly converted from exposure into habitat. The result would be a planet where the geography of life follows moisture with unusual obedience. On the modern Earth, climate certainly shapes where ecosystems appear, but some of the most dramatic transitions between biomes happen over broad gradients, with rivers and groundwater softening the edges. On a rainless Earth, those gradients may sharpen into thresholds. A fog-rich escarpment might support persistent plant cover, and the plateau just beyond it might be almost barren. A spring line might create a green ribbon so narrow that from a distance it looks painted onto the foot of a cliff. An ancient basin with shallow groundwater could host one of the few true inland wetlands, surrounded by dozens or hundreds of kilometers of hard country. The map of life would become a map of hidden water. To know where organisms can persist, you would need to know where the planet still leaks. Such leakage would also define the emotional topography for animals. Before we think of large herbivores or predators, consider the simplest requirement: movement toward water. In wet environments, water is often ambient. It may pool after storms, flow in multiple channels, or sit within the tissues of abundant plants. In a rainless terrestrial world, it becomes concentrated and therefore dangerous. Every reliable source attracts life. Every source becomes a point of congregation, competition, and memory. Animals would learn routes dictated not by seasonal rain fronts, but by fixed hydrological anchors. Paths would form between one damp refuge and another. Migrations, where possible, would be less like sweeping responses to a continent-wide greening and more like calculated journeys across hazard between islands of survival. This creates one of the most primal visions in the entire scenario: the last damp places.
Imagine a shallow, spring-fed basin under a wall of rock, its margins lined with sparse reeds, crusted mud, mineral stains, and a few hardy trees whose roots reach far below the surface. The wider world around it is pale, hot, and acoustically empty. Yet here, tracks overlap. Insects gather.
Small animals arrive at dusk. Larger herbivores, if such creatures exist in this world, come down carefully at first light or in the evening cool. Predators know this. Scavengers know this. Every breath of life in the basin has been pulled there by the same need. Water, once broadly distributed by rain, has become theater, and theater attracts both audience and violence. Modern ecologists often describe dry landscapes in terms of resource concentration, where food, shade, or water are unevenly distributed. Behavior changes, competition sharpens, territory forms around access, daily rhythms become more precise. Predators focus attention where prey must eventually appear. These patterns already exist in some of Earth's driest regions. What changes on a rainless Earth is the scale and ubiquity of the pattern. Instead of being a feature of particular deserts, concentrated water points become the basic rule of terrestrial ecology. That makes land life more brittle. If one spring fails, the effect is not local inconvenience. It is ecological collapse for everything tied to it. The collapse could happen in several ways. A groundwater level might fall as geological pathways shift. Salts might accumulate until once usable soils become hostile. Wind erosion could strip fine material from a wet margin and expose roots. A small temperature change might reduce the persistence of coastal fog. A plant community that stabilized the edge of a seep could die back, accelerating erosion and changing how water emerges. In a humid world, neighboring systems sometimes compensate for one another. In a rainless world, neighboring systems may not exist. The refuges are isolated enough that failure means absence, not redistribution. Because of this, animals in the terrestrial interior would probably face tighter limits on body size, abundance, and range than their counterparts in wetter worlds. That does not mean large animals are impossible.
Some dry regions on Earth can support impressive megafauna, where groundwater, rivers, or seasonal rains are available. But those examples depend on either strong plant productivity during at least part of the year, or access to extensive resources distributed across a landscape. In our scenario, both conditions are weaker. Sparse vegetation means limited primary productivity. Limited productivity constrains the total energy available to herbivores. That, in turn, constrains predators. Food webs remain shorter, patchier, and more vulnerable to interruption. There is also the matter of heat. Dry continents without significant rainfall would not simply be thirsty. In many cases, they would likely be thermally harsh, especially away from the moderating influence of the sea. Earlier, we touched on the long-term climate relevance of weakened weathering and possible difficulty in drawing down carbon dioxide as efficiently as on our own Earth. Now it is worth considering the ground-level experience. Dry soil and bare rock can heat rapidly under sunlight. Sparse vegetation offers little shade. Evaporative cooling is limited because there is little free water in the surface layers to evaporate. The result is not just higher daytime temperatures, but a different quality of heat. Humid heat can be oppressive, but dry continental heat can feel surgical, stripping moisture from skin and breath. Animals exposed to it must solve problems of water balance, shelter, timing, and heat exchange continuously.
Many would do so by shifting activity into cooler hours. Twilight and night could become the busiest periods for the interior fauna. Burrowing would offer refuge where soil or sediment allowed it. Crepuscular and nocturnal lifestyles would be favored. Pale coloration might help reflect sunlight in some regions, while darker tones might still persist where camouflage or heat absorption during cool mornings mattered. Physiological strategies could include efficient kidneys,
Concentrated waste, tolerance for dehydration, and reliance on moisture-rich foods. These are real biological themes visible across many lineages on the modern Earth. Yet again, the question is not whether such adaptations could arise, it is whether they could support broad, diverse, stable terrestrial ecosystems on a continental scale. The answer remains uncertain at best, and probably limited. Meanwhile, the oceans might be telling a very different story. This contrast is easy to overlook because we are so interested in the fate of land, but a planet can be biologically rich without its continents being rich. Marine productivity depends on light, nutrients, temperature structure, circulation, mixing, and coastal inputs, not on rainfall over land alone. In fact, dust from the dry continents could even fertilize parts of the ocean by delivering iron and other minerals, much as desert dust does in some modern marine systems. Coastal upwelling, where it exists, could support abundant life. Continental shelves might remain dynamic, food-rich zones. Reefs or reef-like systems could develop if chemistry and temperatures allowed. The sea would continue to host complexity, even as the land remained ecologically cautious. From the shore, that contrast would feel almost cruel. Behind you, a biologically expansive ocean. Before you, a continent that cannot quite decide to live. This is one reason the edges of this world matter so much. Coasts would not only be zones of moderate temperature and intermittent moisture, they would also be interfaces between two very different scales of life. Marine birds, or their analogs, might nest on cliffs, feeding from rich waters while avoiding the worst of the interior. Shoreline scavengers could move between stranded marine productivity and sparse terrestrial prey. Tidal flats might host concentrated life where the sea literally arrives on schedule, replacing some of the ecological functions that rain performs elsewhere. The coasts would become laboratories of compromise, places where a fundamentally dry continent borrows vitality from the sea. The borrowing, however, would have limits. Salt water is not a replacement for rain. It can support coastal ecosystems adapted to brackish or marine conditions, but it cannot build widespread freshwater soils inland. Nor can fog alone, though fog deserves more attention than it usually receives. On modern Earth, some of the driest inhabited places on land still support life because fog delivers moisture reliably enough to maintain lichens, beetles, shrubs, and even surprisingly complex webs. The Namib Desert is a famous example of a place where fog matters deeply. That tells us something encouraging for the speculative planet. Life can indeed colonize land under extreme aridity if atmospheric moisture repeatedly arrives in forms other than rain. Yet it also tells us something restrictive. Those systems are narrow, fragile, and highly dependent on geography. They do not easily expand into broad continental abundance. So the likely botanical map of a rainless Earth would be a layered one. First, there would be biologically rich marine realms, shaped more by ocean physics than by the fate of the continents. Second, there would be coastal terrestrial belts, their productivity varying with fog, sea spray, local topography, and access to groundwater. Third, there would be rare inland refuges
where geology permits springs, shallow aquifers, or unusual condensation patterns. Beyond that, the dominant texture of land would remain open, exposed, and sparsely alive. The world would have green places, but not a green heart. And without a green heart, the chemistry of the atmosphere might drift differently over time. The spread of terrestrial plants on Earth had deep consequences for carbon burial, weathering, oxygen dynamics, and climate feedbacks. How exactly those processes would differ on a rainless Earth depends on the era,
because Earth's atmosphere has changed immensely across geological time. Yet the principle remains important. Reduced terrestrial biomass means less carbon stored on land. Reduced rooting and litter production means different weathering rates and nutrient cycling. Fewer wetlands and forests mean different patterns of methane and oxygen exchange. The details would be complex, but complexity should not hide the overall message. A dry continent is not just biologically smaller, it is chemically different. This chemical difference could feed back into climate through several routes. Less vegetation means less evapotranspiration, which can reduce atmospheric moisture recycling over land. Dry, bare surfaces often reflect light differently than forested ones. Dust aerosols can affect cloud formation and incoming solar radiation. Reduced silicate weathering may allow atmospheric carbon dioxide to remain higher than it otherwise would. If so, long-term warmth becomes easier to maintain, particularly when paired with weak continental moisture recycling. The land does not merely fail to cool itself through evaporation, it may also fail to participate fully in the deeper geochemical processes that stabilize climate on multi-million-year timescales. A rainless Earth could therefore become not only dry, but persistently predisposed toward warmth. Of course, Earth history reminds us that warm does not always mean uniformly hostile. Some of the warmest intervals in the planet's past supported extraordinary marine life and lush vegetation in regions where moisture was available. The difference is that in our scenario, moisture availability is decoupled from continental breadth. Even on a warm world, a well-watered continent can be biologically exuberant. A warm world with almost no rain over land is something else entirely. It is heat without release, sunlight without softening, and atmospheric energy without a continental harvest. To imagine the long-term appearance of such a planet from space is to see a familiar globe with unfamiliar balance. The oceans would still dominate the surface in blue. White clouds would still pass overhead, perhaps in bands and spirals and diffuse swarms. But the continents might appear less green than at almost any time in the modern era. Their colors would lean toward tan, ochre, rust, gray, and salt white. The branching darkness of river systems would be sparse. Great humid equatorial belts would not spread across land in the same way. Seasonal pulses visible today in vegetation indexes would be weaker, or concentrated near coasts and special basins. Earth, from orbit, would look older than it is, as though the continents had remained in a more primitive state while the oceans continued evolving. That visual impression matters because it changes how we think about habitability. Modern intuition tells us that a blue planet is a living planet, and broadly that is true. But for terrestrial abundance, blue is not enough. The water has to move onto land in sufficient quantities and at sufficient regularity to build soils, support plants, and maintain freshwater networks. A rainless Earth would challenge that intuition. It would still be a water world. It would simply be a world where the continents stand on the wrong side of the exchange.
As we move deeper into this possibility, another contrast emerges, one that would shape the fossil record if such a planet existed for long stretches of time. Wet continental environments are excellent at generating particular kinds of sedimentary archives: floodplains, lake beds, swamps, deltas, alluvial fans linked to rivers, and soils rich in organic traces. Dry worlds preserve differently. Wind-blown sandstones, evaporite deposits, paleosols marked by salt and carbonate accumulation, footprints preserved on drying flats, bones gathered around shrinking water points, fine dust trapped in quiet basins.
The geological memory of life becomes more episodic and more biased toward refuge zones. If paleontologists one day studied such a world, they might reconstruct not a continuous continental biosphere, but a mosaic of living islands separated by enormous taphonomic silence. That silence has emotional force as well. In wet worlds, life announces itself almost casually. A stream runs, insects hover, stems bend, leaves transpire, birds cross from tree line to tree line. In the rainless world, signs of life are often either concentrated or absent. You may travel for long distances and encounter little more than tracks, a few resilient plants, perhaps a dust plume raised by unseen movement, then suddenly come upon a spring basin alive with sound. The contrast would make every inhabited patch feel temporary, even if it had persisted for thousands of years. The continent teaches insecurity not by constant catastrophe, but by withholding continuity. And still, continuity does exist, just in other media. The sea remains continuous, the atmosphere remains continuous, dust remains continuous, geological time remains continuous. What the land lacks is not process, but a specific kind of repeated delivery. This observation keeps the scenario scientifically grounded. We are not imagining a magical curse on life. We are exploring how one missing branch of the water cycle cascades through geology, climate, and ecology. The more carefully we follow that cascade, the clearer it becomes that rainfall is not an ornament on terrestrial existence. It is one of its structural supports. That is why the dry planet becomes more unsettling the more seriously we take it. A child might say, quite reasonably, that without rain, everything would just be desert. Science asks for a more exact answer. Which deserts? Fed by what? Bordered by what? With what groundwater? Under what atmospheric composition? With what oceanic consequences? The refined answer is richer and stranger. Not everything becomes the same desert. The world differentiates sharply into marine abundance, coastal compromise, hydrological refuges, and vast exposed interiors. Life survives, perhaps even flourishes in special places, but the land as a whole never fully joins the biological richness of the sea. What makes the failure of soil formation so decisive is that soil is one of the few places where geology and biology truly overlap in slow motion. Rock belongs to deep time. Leaves belong to short time. Rain helps them speak to each other. When drops soak into a surface, they are not only carrying water, they are carrying delay. They slow the loss of organic matter by hiding it under moisture and sediment. They allow dissolved nutrients to move into root zones and microbial films. They make the upper part of the crust less like a wall and more like a sponge. Without that repeated soaking, the uppermost layer of land remains more exposed to extremes and less capable of holding a memory of life. Each generation of organisms must begin closer to zero. That phrase matters here because ecosystems become powerful when they inherit. A forest floor inherits litter.
A grassland inherits root-rich soil. A wetland inherits soft sediment and stored carbon. Inheritance makes expansion easier than first arrival. On this rainless Earth, many terrestrial communities would be denied that advantage. Even when a patch of vegetation succeeds near a spring or in a fog belt, it does not automatically create a broad legacy for the ground beyond it. The next meter away may still be too saline, too shallow, too wind-stripped, or too dry. So life is constantly successful in pockets, yet repeatedly blocked at edges. The continent becomes a place of beginnings that struggle to become continuities. There is a quiet cruelty in that. A cluster of plants can trap a little more dust, darken the ground, and create a cooler microclimate beneath itself. That cooler patch can help seeds survive,
which may increase local cover and deepen the organic layer. On the real Earth, rain often magnifies these small successes until a slope, a basin, or an entire region changes character. Here, the amplification is weaker. A good year, if years can be called good in a world without rain, may be little more than a slightly stronger fog season or a steadier output from a spring. The gain is real, but narrow. The land does not often reward improvement with abundance. It rewards it with temporary persistence. The first large plants attempting to spread inland would therefore face a dilemma that is both physiological and geographic. If they remain small and low to the ground, they can reduce exposure and survive with less water, but they also alter the wider environment only modestly. If they try to grow tall, with larger transport systems and greater demand, they require a supply the atmosphere seldom grants. Trees in our world are, in a sense, vertical monuments to reliable water movement. They can pull moisture upward because the ground below them is periodically recharged. In the rainless interior, only places with dependable groundwater could support anything like that. Most broad uplands and plains would simply not provide the hydraulic foundation for a forest, no matter how long evolution worked at the problem. This helps explain why the missing green world is not just a missing color, but a missing climate engine. Forests moisten air, cast shade, alter turbulence, and generate habitats layered in height and darkness. Grasslands, though lower, still transform the movement of heat, water, and animals across a region. Remove those engines from most continents, and the atmosphere above land remains comparatively simple. Air passes over warm surfaces that give back little moisture. Dust rises. Temperature contrasts sharpen. Local weather patterns still exist, but they lack the feedback of expansive vegetation. It is one more way in which the land remains physically present, yet functionally diminished. For animals, this means that shelter itself becomes a rare resource. In a forested world, shade is cheap, cover is abundant, nesting and hiding places occur in almost every direction. In a largely barren world, shelter is tied to topography, to the few plant communities that persist, or to the ground beneath the surface. Burrows, crevices, cliff shadows, and reed beds around water become disproportionately important. Predation would be shaped as much by access to cover as by access to prey. The open distances between refuges would expose both hunter and hunted. Some species might evolve to cross them quickly. Others might avoid them almost entirely, compressing their range around a single hydrological node and becoming prisoners of its stability. That compression changes behavior in ways that would leave a different emotional trace on the planet. Imagine dawn at one of those rare inland seeps. Herbivores, or whatever analogs this world evolves,
arrive tense and alert, not only because predators may be near, but because there are only so many angles from which one can approach safety. The path is known. The time is known. The danger is therefore known. In wetter worlds, uncertainty often lies in where water will be found after a storm, or in which patch of meadow has greened. Here, uncertainty lies in whether the one place that matters is still functioning today, and who else has already arrived. A geologist standing beside that seep would notice something else as well. The sediments there would be unusually informative. Fine particles would accumulate because water slows wind-blown dust and allows heavier grains to settle. Organic traces might build up. Salts could precipitate in layers. Footprints might press into damp mud and dry into record. Bones, shells, fecal pellets, pollen from the few local plants, insect remains,
and mineral crusts could all become part of a compact archive. Such archives would be invaluable windows into the living continent, precisely because so much of the surrounding land would preserve mostly absence. In a strange way, the rare water points would become the libraries of terrestrial history. Their importance would increase during long, warm intervals. If atmospheric carbon dioxide remained elevated because continental weathering was weaker, and if vegetation never spread widely enough to create strong moisture recycling over land, then hot phases could endure with unusual severity in the interior. During such times, coastlines might still be habitable, and oceans might remain ecologically rich, but the middle of continents would become even more selective. Species would either retreat toward the edges, descend toward groundwater, or disappear from large regions altogether. The land would breathe in contractions, not expansions. Its habitable zones would shrink and loosen again with geological shifts, but rarely burst outward into continent-wide abundance. Seen from very far away, then, this world would not be empty. It would be asymmetrical. Most of the planet's life would be concentrated either in the sea or in narrow ribbons, patches, and nodes where water touches land despite the failure of rain. That pattern would make the continents look less like continuous homes and more like vast barriers interrupted by sanctuaries. And once a world develops that sort of geography, every future possibility on land, from giant food webs to long migrations to the eventual rise of a tool-making intelligence, must begin by answering the same harsh question: how do you build anything large, enduring, and connected on a surface that never learned to drink? The practical consequences for evolution on land are severe. If plant cover remains sparse across most interiors, then large herbivore guilds are difficult to support. If large herbivores remain limited, so do the predators that depend on them. If fresh water is concentrated, then ranges are fragmented and dispersal corridors are narrow. If soils stay poor, then recovery after disturbance is slow. If climate remains warm and dry, then physiological stress is constant. Under such conditions, terrestrial evolution could still be inventive, but it would likely be conservative in scale, localized in opportunity, and repeatedly hemmed in by the same physical constraints. At the same time, there might be extraordinary specialization. Refuges often produce biological originality because selection is intense and niches are unusual. Fog harvesters, burrowers, dormancy specialists, animals able to travel great distances between water points, plants that exploit saline margins or deep groundwater, coastal scavengers linking ocean productivity to land food webs.
organisms whose life cycles unfold in hours when condensation appears and then retreat again into dormancy. This world might lack vast inland forests, yet still produce forms that feel uncanny, precisely because they are tuned to scarcity with such precision. The beauty of evolution under pressure is that it does not surrender easily. It improvises. It narrows its ambitions, but refines its tools. Even so, a refined survival strategy is not the same thing as a transformed planet. That transformation remains incomplete. The continents still look chemically underdeveloped, biologically thin, and hydrologically fragmented. They have not been conquered in the way our own were. The great inland carpets of green that on Earth eventually altered weather, rivers, soils, and the atmospheric story itself remain largely absent. There are damp places, there are living edges, there are perhaps even isolated inland wonders, but there is no broad terrestrial engine matching the ocean in scope. And because there is no such engine, the question of scale returns once more, now sharper than before.
Could a world like this ever host the kind of large terrestrial dramas that shaped our own imagination of prehistoric Earth? Great herds crossing plains, vast forests feeding huge bodies, inland predators ruling river valleys, seasonal explosions of growth over millions of square kilometers. Those images depend on energy captured on land and spread across land. A rainless Earth, at least in the version we have followed so far, offers too little distribution. It may produce intensity, but not expanse. It may produce life, but not a deeply vegetated continental stage. By the time night falls over such a continent, the difference becomes almost philosophical. The heat drains from the ground, the sky clears, stars sharpen in the dry air. Around a rare water source, life stirs again, cautious and deliberate. Elsewhere, the land returns to stony stillness. You begin to sense that the missing rain has done more than reduce comfort or fertility. It has changed the emotional logic of the planet. The sea feels full. The land feels conditional. Survival depends not on inhabiting a generous surface, but on finding the exceptions hidden within it. Those exceptions will matter even more when we turn from the ecology of refuge to the possibility of something larger and more unsettling. If the land cannot easily green itself, if its water remains concentrated, if its soils stay young and poor, then every later chapter of terrestrial history must be reinterpreted. The rise of large animal communities, the expansion of food webs, the possibility of long inland migrations, the emergence of landscapes rich enough to sustain complex social life, and eventually, the question of whether an intelligent species could ever treat these continents as home rather than obstacle. All of that waits ahead, and to approach that question honestly, we have to carry forward the world exactly as it is now. Oceans rich, coasts alive, interiors severe, and the great missing gift of rain still hanging, silent and unresolved in the sky. One answer might be time itself. Given tens of millions of years, life can exploit very narrow advantages. A root that reaches a little deeper, a seed that waits a little longer, a burrow that holds humidity a little better, a microbial film that binds dust a little more tightly. All can matter. Yet, time cannot repeal physics. It can only explore within it. So, even after ages of adaptation, the central fact remains. The sky does not deliver broad freshwater renewal to the continents. That missing renewal keeps every terrestrial experiment bounded. It allows innovation, but restrains enlargement,
It permits refuge, but resists empire. And that is why, before we ask what kinds of creatures or civilizations might emerge here, we first have to accept the physical scale of the restriction, because everything that follows on land grows in the shadow of that one absent descent. The continents are broad, ancient, and magnificent, but magnificence is not the same as hospitality. Until water can move inward in abundance, rock remains mostly rock, life remains mostly local, and the planet's terrestrial possibilities stay suspended just beyond reach. And because every terrestrial experiment on this planet must grow beneath that absent descent, the next question is almost impossible to avoid. Could land life ever become truly large here? Not just specialized, not just local, but expansive enough to dominate a continent in the way forests, grasslands, and great animal communities have done on our own Earth. It is a question that sounds simple until you follow the arithmetic of life itself. Size is not only anatomy. Size is stored sunlight. It is water gathered into tissue, nutrients pulled upward through roots or swallowed through food, and enough stable energy moving through an environment that bodies can become abundant, then complex, then immense. In the rainless world, that arithmetic never stops being difficult. On Earth,
Large terrestrial ecosystems depend on primary productivity spread across distance. Plants must capture light at scale and convert it into edible or decomposable matter. Herbivores must then be able to move through landscapes where that productivity is renewed often enough to support large bodies and large populations. Predators require prey dense enough to hunt without exhausting the land. Even scavengers depend on the surplus of a food web rich enough to generate death in useful amounts. All of this is easier when water is not hidden in isolated pockets, but woven through the ground, the air, and the seasons. Rain does not create all terrestrial life, but it lowers the cost of being terrestrial. Remove it, and every increase in size becomes more expensive. That does not mean the land must remain permanently small in every corner. If some coastlines are fed by steady fog, if some tectonic regions leak groundwater for millions of years, if some basins store enough hidden water to support persistent plant communities, then parts of the continent could become richer than the broad picture suggests. In those places, one can imagine woodland-like belts, reed-filled wetlands, shrubby uplands cooled by marine air, perhaps even patchy forests above extensive aquifers. The real Earth offers hints that such local abundance is plausible. Oases, spring-fed valleys, cloud forests on mountain slopes, and coastal ecosystems in otherwise dry countries all show how life can become surprisingly lush where moisture is concentrated by geography. So the answer is not absolute impossibility. It is confinement. Great terrestrial life might arise, but it would arise in enclaves. The fate of body size would therefore vary sharply with habitat. Small forms are usually more resilient in water-stressed environments because they need less total intake, can hide from heat more easily, and can exploit brief or patchy food sources. Large animals can endure scarcity too, but only if they can travel efficiently between resources, or if those resources are sufficiently predictable. Elephants, antelope, camels, and other large animals in dry, modern landscapes survive because they inherit worlds where rivers, seasonal rains, deep-rooted vegetation, or long-evolved migratory networks still connect survival across space. In the rainless world, those connections are weaker and often broken. A large herbivore would need a dependable circuit linking one productive refuge to another, and the longer that circuit becomes, the greater the danger between each point. Water and food are not merely scarce, they are discontinuous. This discontinuity shapes evolution in a subtle way. Once a lineage becomes large, it must keep earning that size. Big bodies can offer advantages: heat retention overnight, resilience against some predators, the ability to travel farther, the ability to digest coarse vegetation, the ability to store water or energy differently. But they also commit an animal to a landscape broad enough to feed it. On a rainless continent, broad landscapes may exist physically while remaining functionally unusable. A plain can stretch for hundreds of kilometers and still be, in biological terms, almost empty. A giant wandering into such emptiness would not meet the generous meadow of a seasonal world. It would meet distance, reflected heat, and a horizon that promises nothing. Over time, selection might therefore favor animals that are either small enough to live close to refuge or specialized enough to move efficiently from refuge to refuge without depending on lush country between them. That may produce a terrestrial fauna unlike the one most people imagine when they think of prehistoric grandeur. Instead of vast inland herbivore herds feeding apex predators across productive plains, there may be narrower communities clustered along spring-fed corridors, coastal fog zones, or the margins of inland groundwater lakes.
Large browsers could exist where woody vegetation persists over aquifers. Fast-moving grazers might appear in certain moist depressions if grass-like plants evolve there. Predators would shadow those systems closely. But the interior heart of continents would remain hard to occupy at high density. Gigantism would be possible in places and improbable in most others. The truly dominant giants of this planet might remain marine, where the ocean continues to distribute energy on a scale the land cannot match. There is another reason to be cautious about the rise of great land creatures. On the real Earth, large, stable ecosystems often depend on layered freshwater systems. Water falls as rain, gathers in soils, infiltrates into groundwater, runs into streams, and returns through plants into the air. Animals drink from some part of that chain, but the chain itself also keeps vegetation alive. If a spring on a rainless world depends on deep geological plumbing rather than a recharged watershed, then its persistence may be measured more by subsurface inheritance than by surface renewal. That makes the system vulnerable over evolutionary timescales. A lineage that grows large around one long-lived basin may flourish for hundreds of thousands or millions of years, but if the groundwater pathway shifts, the ecological foundation could vanish with little warning. Rain, by contrast, spreads redundancy. It allows one region to fail, while another survives. It creates alternatives. In the dry world, alternatives are fewer. Perhaps the most plausible large terrestrial ecosystems, then, would occur where the dry continent is interrupted by special geometry. Imagine a mountain range close enough to the sea that cool air, frequent fog, and hidden groundwater together sustain a chain of elevated valleys. There, over long ages, plants might thicken the soil, local streams of spring water might connect wetlands, and a corridor of relative richness could emerge. In such a corridor, animals larger than anything in the surrounding desert might evolve. They would still live under limits, but to an observer crossing the outer plane, they would seem like emissaries from another planet, creatures of shadow and leaf in a world otherwise made of glare. The very existence of such refuges would intensify the contrast between abundance and emptiness. Outside the corridor, life would shrink again toward austerity. This pattern also influences intelligence, because intelligence on land is not only a question of brain tissue, it is a question of ecological opportunity. Large brains are energetically costly. Complex social life often flourishes where environments provide enough stable resources to support extended development, learning, memory, cooperation, and experimentation. Humans did not evolve in a single lush paradise, but within dynamic landscapes where water, vegetation, and mobility were sufficient to make flexible social intelligence advantageous. If land on the rainless Earth remains fragmented into isolated productive patches divided by severe distances, intelligence could still evolve, but it would likely do so under a different set of pressures. Before we reach that possibility, though, it is worth considering a more immediate implication. What would it mean simply to be a terrestrial omnivore, clever enough to range widely, yet born into a continent that never learned to drink? Such a creature would inherit a map of fear. Not fear in the poetic sense alone, but in the literal neurological logic of survival. Fear of leaving the coast too late in the day. Fear of trusting an old water path that has gone dry. Fear of walking into a basin ringed by tracks, because tracks mean thirst has brought many bodies to the same place. Fear of cloud buildup that never becomes relief, because expectation itself becomes a kind of wound. On our Earth, people in very arid regions often organize movement, memory, myth, and technology around water scarcity. Springs, wells, flood channels, and seasonal pools shape routes, alliances, and rituals. This is not speculation. It is a recurring pattern in human history. On the rainless Earth, that pattern would begin earlier and bite deeper. Water would not be one important resource among others. It would be the organizing principle of land society from the start. If beings like us ever appear here, they are unlikely to arise in the continental interior. The physical probabilities point instead toward margins where biological productivity, habitat complexity, and environmental variability overlap without tipping into total sterility. Coasts are the strongest candidates. There, marine food webs provide protein and fat. Fog, dew, and groundwater increase the chances of persistent vegetation. Temperatures are moderated by the ocean. Topographic diversity creates niches. Materials from sea and land alike can be used. In many parts of our own history, coastlines were powerful habitats for early humans and later civilizations, though they were never the only ones. On the rainless Earth, they might become the primary cradle of terrestrial intelligence. That would give rise to a civilization whose first lessons are maritime and hydrological at once. Children would learn the smell of salt before they learn the smell of wet earth, because wet earth hardly exists. They would know tides better than thunderstorms. Clouds would be watched not for rain, but for shade, fog, or changes in wind. Fresh water would be found in seeps, springs, gathered condensation, carefully protected lenses within porous ground, or deep wells dug where geology permits. The sound of dripping from a rock overhang might carry a significance no lush world could understand. It would not be background, it would be inheritance. As populations grow,
Settlements would almost certainly cluster around permanent freshwater sources or dependable methods of capturing atmospheric moisture.
Coastal springs would become sacred long before they became political. Later, they would become political as well. If a shoreline offered shellfish, fish, seaweed, and the moderating influence of marine air, but only one spring within walking distance, then that spring would anchor not just a village, but memory, law, kinship, and conflict. Control of water would be power in the most basic possible sense. It would decide where walls could be built, where grain or grain-like crops might be attempted, where animals could be kept, where trade routes could begin, and who was forced to move when output fell. Technological ingenuity in such a world would likely focus first on conservation rather than expansion. Containers, cisterns, channels, coverings, underground storage, fog nets if the culture reached that idea, stone-lined basins to reduce seepage, methods of shading water, ways of protecting recharge zones and springs from contamination, social rules about access, calendars tied to mist seasons rather than rain seasons. Agriculture, if it emerged, would be constrained by the same reality. Irrigation is possible only where water exists to be diverted. On our Earth, many early civilizations developed sophisticated irrigation in dry climates, but they usually relied on rivers fed by distant rainfall or snowmelt, or on predictable flood pulses. A world without those broad river systems offers fewer such opportunities. Farming might remain intensely local, attached to groundwater-fed oases or coastal zones where condensation and engineered storage can just barely support crops. This would produce settlements that look stable from a distance and fragile up close. Stone houses might cluster around a well. Terraces might climb a foggy slope. Reed beds might mark a hidden seep behind a cliff. Yet every one of these places would know that its permanence is conditional. A dry year would not be unusual enough to fear because dryness is normal. What would be feared instead is the small deviation within dryness, the weak fog season, the lowered spring output, the salting of soil, the collapse of a well shaft, the taste of minerals changing in stored water. On our Earth, many cultures imagine apocalyptic drought as the withdrawal of what is usually given. In this world, the apocalypse would be quieter. It would be the slight failure of the little that was ever available. Because of that, the deep interior of continents might remain half mythical, even to an advanced coastal civilization. Exploration could occur, of course. People cross deserts, they map routes, they quarry minerals, they hunt, trade, raid, and wander. But if inland travel requires precise knowledge of hidden water points and offers little permanent habitability in return, then the interior becomes more frontier than homeland. It could be rich in ores, salt, pigments, fossils, and hard stone, perhaps even revered for its clarity and silence, yet it would not easily become the dense civic landscape familiar from river valleys and rainy lowlands on Earth. The center of the continent would remain a space of extraction, ordeal, pilgrimage, or exile, not one of effortless settlement. This changes the cultural imagination as much as the economy. In a rainy world, the sky can be a giver, an interrupter, a destroyer, or a blessing. In a rainless world, the sky becomes a refusal, not because clouds never form, but because they form and still withhold. Religions, myths, and philosophies might therefore focus intensely on thresholds and withheld abundance. The sea would represent visible fullness,
but unusable water. The clouds would represent the promise of water, but not its arrival. Springs would represent hidden mercy from the ground, rather than grace from the sky. A civilization shaped by such conditions might worship what emerges rather than what falls. Wells would feel older than temples because, in a practical sense, they are.
The political consequences could be severe. If the main bottleneck to settlement is water access, then hierarchy can be built around proximity to freshwater infrastructure. Control the well, and you control the square around it. Control the spring, and you control the terraces below it. Control the fog-catching ridges, and you control the only slope where orchards are possible. Such systems need not always be tyrannical. They could also produce intricate communal law, seasonal sharing, or sacred protections for hydrological sites. But the pressure toward centralization would be strong, because hydraulic fragility favors organized management at the same time that scarcity invites domination. The history of water control on Earth already shows this repeatedly. On the rainless Earth, the pattern would reach deeper into ordinary life. Trade networks would likely follow moisture chains along coasts and between refuge zones, rather than cut boldly across interiors. Ports, spring towns, and mineral outposts could form a necklace around continents, connected more by sea than by land. Maritime culture might advance early, not only because the sea feeds people, but because ships bypass the thirsty distances that make inland transport difficult. Civilizations could become sophisticated without ever greenly filling the interiors behind them. The cultural map might look more like a luminous edge than a solidly inhabited mass. History would happen along rims. And yet humans, or whatever analogs emerge, are often driven by something other than efficiency. Curiosity sends them inward. Fear sends them inward too, because what is unknown in the interior can threaten the edge in imagination long before it does in fact. So expeditions would cross these dry continents. They would follow canyons that hold old traces of groundwater. They would seek fossil aquifers, mineral flats, and vanished basins.
They might find astonishing remnants of earlier ecological experiments. Forests turned to stone around long-dead springs, lake beds packed with bones from a refuge that failed, dunes preserving the footprints of creatures that once moved between now separated basins. To such explorers, the interior would seem not empty, but arrested, full of unfinished attempts by the planet to become something gentler. That sense of arrest brings us back to the central scientific lesson of the entire thought experiment. The reason rain matters so much is not only that living things need water, it is that rainfall links scale to continuity. A spring can support life. Fog can support life. Dew can support life. Groundwater can support life. But rain alone, in ordinary planetary experience, turns the sky into a widespread distributor. It carries moisture beyond immediate coasts and exceptional leaks. It allows ecosystems to inherit from one another across distance. It allows soil to deepen over plains, plants to spread beyond refuges, rivers to connect mountains to seas, and civilizations to rise far from the edge of the ocean. Without it, the terrestrial world becomes talented, but provincial. That does not diminish the beauty of the life that would survive here. In fact, it may intensify it. A small grove around a spring on a rainless world would feel more miraculous than an ordinary forest on our own. The first shadow cast by its leaves would carry geological significance. A large animal stepping out from that shade at dusk would seem improbably precious,
not because it is cute or rare in the sentimental sense, but because so much chemistry, hydrology, and time had to align for that body to be possible at all. In a dry civilization, tenderness toward water and shade might not be moral preference. It might be a practical form of wisdom learned so deeply that it becomes art. One can imagine cities built accordingly, not sprawling green capitals fed by mighty rivers,
but compact settlements of stone, plaster, and shadow, organized around courtyards, cisterns, wells, condensation towers, and subterranean storage, rooflines designed to gather dew, streets narrow enough to keep sunlight off the ground for part of the day, public life timed to marine breezes or evening cool, gardens hidden behind walls where every leaf has been paid for in labor. The architecture of such places would not only respond to scarcity, it would speak it. Water would be heard before it is seen. A basin in a central court, barely rippling, might hold the emotional weight of an entire square. Beyond those walls, perhaps only a few hours inland, the old severity would still wait. That is what would prevent such cultures from forgetting their dependence. A wet empire can become complacent because abundance looks natural. A dry-edge civilization cannot. It knows exactly where the living world ends. It knows how quickly a journey can pass from habitable into hostile. The horizon itself becomes ethical. To waste water would feel not merely foolish, but disrespectful to the conditions that permit community at all. If intelligence never appears, all of these cultural possibilities disappear, of course. The world remains a biological puzzle rather than a civilizational one. Yet, even then, the thought experiment has already done something important. It has shown that intelligence like ours is not an obvious destiny for every ocean-bearing planet. Water in the sea is not enough. Atmosphere is not enough. Continents are not enough. The path toward a rich terrestrial biosphere, and perhaps eventually toward a species capable of asking questions about its own world, depends on specific physical relationships being maintained over immense time. Rain is one of those relationships. It is not the only one, but it is central. This realization changes how we see our own planet. In ordinary life, rain can seem irritating, repetitive, almost beneath notice, unless it becomes dramatic. We complain when it delays us, when it blurs a view, when it turns a road slick, when it keeps us indoors. But from the perspective of deep time, rain is one of the quiet miracles of habitability. It is the repeated act by which the sea shares itself with the land. It is how mountains are softened into soils, how forests are fed far from coasts, how aquifers are replenished, how rivers begin, how valleys are written, how wetlands persist, and how the interior of continents becomes more than exposed stone. There is a paradox here. The hypothetical world we have followed is, in one sense, more dramatic than our own. Its coasts are precious, its refuges tense, its interiors severe. It feels primal because need is visible. Yet the real Earth may be more extraordinary precisely because its daily generosity is so easy to overlook. A cloud thickening over a distant hill, a cool front moving in, the smell of dust turning to soil, water falling through leaves, soaking into dark ground, feeding a stream that no one will notice from source to sea. These are not decorative details. They are expressions of planetary success. When you think about it that way, the whole history of terrestrial life begins to look less inevitable
and more contingent. The forests of the Carboniferous, the floodplains of the Cretaceous, the grasslands that later fed great mammals, the river valleys that nourished human settlements, all of them depend on the atmosphere doing more than merely exist above land. It must collaborate with land. It must deliver. If the clouds gather and never give, then even with oceans, rocks, sunshine, and time, the continents remain diminished. Life survives, it adapts, it invents, but it builds under restraint. This is one of the deepest lessons hidden inside speculative questions. A good what-if scenario is not really an escape from reality. It is a method of revealing which parts of reality matter most.
By removing rain, we discover not only how dry a world could become, but how much of our own world has been shaped by something so common that we rarely elevate it in our minds. We notice the hidden architecture precisely because we imagine its absence. The bare continent teaches us what the wet one was doing all along. It also invites a more patient view of time. Geological processes do not hurry. Weathering, soil building, ecological spread, and climate feedbacks unfold across spans so large that human history is almost invisible against them. Yet these vast processes are built from repetition. One wetting, another, then another, until rock softens, roots enter, channels form, sediment moves, and a world becomes habitable in ways no single storm could claim credit for. The rainless earth lacks that repetition. Its tragedy is not one catastrophe. It is the endless non-arrival of a small event. In that sense, the thought experiment feels strangely intimate. Whole continents are changed by what never quite happens. Even the emotional life of a being born there would differ in ways difficult for us to fully inhabit. On Earth, anticipation of rain is often hopeful. Farmers watch the sky. Children wait for the first storm of a season. Cities breathe easier when reservoirs refill. There is anxiety, too, of course, and danger. Yet embedded in our psychology is the expectation that the sky may, at times, answer. In the dry world, expectation would need to detach itself from clouds. Hope would be tied to stone, depth, fog, and memory. A spring would be more trustworthy than a horizon. Perhaps even language would reflect that, filling itself with words for seepage, mineral taste, underground sound, coastal dampness, and the many shades of thirst. By now, the image of the planet has become almost complete. Oceans glitter under wide, moving skies. Along certain coasts, fog enters at dawn like a soft procession, silvering rocks and feeding narrow belts of life. In a few inland basins, groundwater reaches the surface and momentarily gathers the living around it. Elsewhere, the continents lie pale and vast, ridged by old uplift, crossed by wind, littered with salts, their soils thin, their vegetation uncertain, their great interiors more like waiting than fulfillment. If there are cities, they cling to margins and hidden water. If there are myths, they begin with wells. If there are large animals, they know the map of refuge better than the map of land. And above all of it stretches a sky still performing half of a cycle, carrying moisture, forming clouds, but never completing the quiet gift on which terrestrial abundance depends. At this point, the question of us, the question implied from the very beginning, can finally be faced without forcing the answer. Could a world like this produce beings like us? Perhaps, in some form, under the right sequence of accidents and adaptations. Intelligence does not require forests alone.
nor does technology require endless rivers. But a world like this would make such an outcome harder, narrower, and more coastal. It would reduce the number of routes by which terrestrial complexity could grow. It would make large inland biospheres less likely, agriculture more constrained, settlement more hydrological, and expansion more dependent on maritime skill than on continental generosity. If minds like ours arose, they would arise in the shadow of scarcity and remain aware, far longer than we have, that land itself is not automatically kind, and that may be the most humbling answer of all. Human intelligence, in our own history, often behaves as though the planet was prepared for us. The deeper truth is stranger. We are the late consequence of many physical successes that did not have to happen in the way they did. One of those successes is so familiar that we walk through it without noticing. Rain fell. It fell on mountains and plains, on young continents and old ones,
on volcanic rock and leaf litter, on empty channels that became rivers, on dust that became soil, on seeds that became forests, on the long inland corridors that later became habitats, then pathways, then homes. If the rain had not come, perhaps thought itself on land would have remained rarer, more local, more hesitant. There is comfort, strangely enough, in seeing that dependence clearly. It restores scale. It reminds us that the world is not built from dramatic singularities alone, from asteroid strikes, supervolcanoes, or sudden extinctions. It is also built from repetitions so gentle they feel almost invisible. Drops darkening stone, water slipping into roots, a stream beginning somewhere out of sight. The ordinary is sometimes the deepest architecture. Now, as the journey quiets, the dry planet grows still again in the mind. The settlements, if any are there, draw in their lamps. The wells rest under stone rims polished by many hands. Along the coast, fog drifts inland and thins over the first low ridges. In a hidden basin, a spring continues to rise from darkness below, not loudly, just enough to keep a narrow fringe of green alive through another night. Farther out, the open continent cools beneath the stars. The salts pale, the dust settles. The old mountains stand with their dry valleys folded between them, waiting for a rain that never belonged to their history. And above them, clouds move in silence, carrying the sea across the sky without ever laying it down. That is the image that remains. Not catastrophe, not fire, not destruction, but a world suspended in near completion, a planet where the ingredients of abundance are present, and yet the final exchange is missing. The oceans breathe, the atmosphere turns. Life persists where it can, the land endures. But the deep interior of the world stays outside the circle of easy generosity, held at the edge of becoming by a sky that never opens. If you stay with that image a little longer, the real earth begins to feel almost impossibly tender. Rain on leaves, rain on rooftops, rain crossing an empty field at dusk, rain pooling in tracks, sliding into streams, feeding roots no one sees. The sound of it reaching ground is the sound of continents being included, and in the vastness of geological time, that inclusion may be one of the quiet reasons we are here at all. So the dry world continues, far beyond the reach of our words, its coasts silvered by fog, its wells deep, its cities careful, its animals tracing old routes between hidden water and shade, its interiors gleaming with salt and moonlight, its mountains cut by valleys that never learned the language of rivers. It is a beautiful planet, but a withheld one, a planet where the sea and sky remain in conversation while the land listens from a distance. There is one last angle worth holding before the silence settles completely. A world without rain also changes the meaning of season. On Earth, seasons are often felt through water as much as through temperature. A wet season greens a slope. A dry season empties a channel. Snowmelt swells a river. Then summer lowers it. Rain tells plants when to grow quickly, animals when to breed, and insects when to emerge. In the withheld world, time would still turn through orbit, tilt, and light, but many of those rhythms would be flatter on land. Heat might rise and fall. Fog belts might strengthen or weaken with currents and winds. Springs might pulse slightly with deep geological pressure or coastal recharge. Yet the renewal that rainfall gives to terrestrial systems would remain muted. The calendar of the continent would be a subtler, harsher thing, marked less by flourishing than by degrees of endurance. Memory would live differently there too. In a rainy world, many landscapes heal quickly. Bare soil greens over. Dust is pinned down. Tracks vanish. Streams redraw themselves after floods. In the rainless world, memory clings to the ground. Paths endure. Abandoned walls stand longer. Dry channels remain legible as old hopes of flow. Bones whiten slowly in open basins. The land keeps its records because so little arrives to soften them. A civilization living in such conditions might become unusually conscious of traces. It would read history from exposed surfaces the way river cultures read history from layers of mud and silt. The continent would be an archive written not in sediment brought by floods, but in marks preserved by their absence. There is also a cosmic humility in that image. We often imagine life as the main event and geology as the stage beneath it. But on this planet, geology keeps reminding life who prepared the limits. A spring exists because rock layers meet. A fog forest survives because ocean current, topography, and wind happen to align. A city endures because an aquifer was stored under conditions no citizen alive can remember. Nothing on land is fully autonomous. Everything depends on arrangements set in motion long before any creature could notice them. The more intelligent a species becomes here, the more clearly it would see that dependence. Progress would not feel like mastery over nature. It would feel like negotiation with a world that remains fundamentally unmoved by desire. And perhaps that is why the question at the heart of this thought experiment lingers after the logic is complete. It is not only a scientific question about climate, weathering, soils, and ecology. It is also a question about what makes a planet feel hospitable rather than merely habitable. A world can support pockets of life and still refuse to feel welcoming. It can contain oceans, atmosphere, chemistry, and beauty, yet remain emotionally austere because abundance never reaches the ground in ordinary ways. Rain does more than enable biology. It softens existence. It blurs sharp distances. It turns hard surfaces dark. It lets the sky participate in intimacy. Without that intimacy,
Even survival retains a loneliness. A spring is precious, but it is also isolated. A fog belt is alive, but it is narrow. A fertile basin is beautiful, but it is ringed by warning. The land never loses the feeling of being mostly beyond invitation, and that is why the dry world remains gently tragic. Not tragic in the sense of spectacle or ruin, but in the quieter sense of potential repeatedly held back. The rivers almost happen. Civilizations almost happen. The planet stands forever on the threshold of more, and still it waits. That realization does not diminish wonder, it deepens it. Rain tapping against a window, darkening a path, or slipping into a gutter can be understood as part of a story much older than weather reports and larger than inconvenience. It is the old exchange continuing, sea to sky, sky to land, land to life, life back to sky. A patient circulation that keeps continents from remaining only exposure. A circulation that teaches rock to hold memory in the form of roots, streams, forests, and eventually questions. And in the withheld world, where that circulation never fully closes over land, the questions remain too, but they rise from edges, from wells, from salt flats under moonlight, and from the pale outline of a coastal ridge catching fog before dawn. They rise from lives spent close to the few places where the planet remembers how to be generous. Then they drift outward over the long quiet of the interior, where the dust waits, the stone cools, and the horizon keeps its distance.